Hello, my name is Jonathan Chan. I'm a master's student at UBC, and I'll be talking about my work on a syntactic model for a size-dependent type theory. First of all, dependent types are used by a lot of modern theorem provers that are founded on the types as propositions paradigm, where type checking corresponds to checking a proof in some logical system. To ensure that type checking is decidable and that the logic is consistent, for many type theories of theorem provers such as Agda or Coq or Moore, they have to ensure that their recursive functions are terminating. This is currently done using syntactic checks, ensuring that the functions are structurally recursive and recur only on syntactically smaller arguments, but sometimes this is too restrictive. Some checks will also inline definitions along the way, but then this makes definitions non-modular, and even minor syntactic changes can affect whether later functions pass the check. Instead of these checks, another option is to use a type-based termination checking method called size types, where inductive types carry additional size information, and constructors build inductives with larger sizes. In fixed points, recursive calls have to be done on arguments with smaller sizes so that they terminate, and type checking will guarantee this with no additional syntactic checking required. There's a fair amount of relevant past work on size types falling roughly into three groups, covering various combinations of dependent types, higher ranked size types, and bounded size quantification, but to my knowledge there is no work that covers all three, so my work seeks to fill this gap with a higher rank size-dependent type theory with bounded size quantification. In short, this is the generalized calculus of constructions with size types, naturals, W types, case expressions, and fixed points. To show that the theory is consistent, I use a syntactic model in extensional CIC, or CICE, which is a standard, well-studied dependent type theory. The syntactic model is essentially a type-preserving compiler from the source type theory into CICE, and with this model, since we know that CICE is consistent, an inconsistency in the source would compile to one in the target, which would therefore be a contradiction. And in the model, size expressions translate to an inductively defined representation of ordinals, along with a representation of the less than relation on them, and naturals and W types translate to their corresponding inductive definitions, but parameterized by size. The interesting part of the translation is fixed points, which is shown on this slide. They now translate to applications of well-founded induction on sizes. Proving that the translation is type-preserving is still ongoing work. One notable challenge is ensuring that the universe levels of all the inductive types are correct, and other future work include handling general inductives, co-inductives, and the infinite size. If you have any questions or if you want to learn more, be sure to drop by the SRC discussion session. Thanks for watching.